and welcome. So, practical stuff. Let's briefly discuss what we had last week. Okay, so the main thing, I had some uploads to the forum, which were single graphs and not much text, so it's a bit difficult to interpret that. So we will rely on your memory from last week just to have something to say about. Oh, thank you very much. Just to be able to say something about what we've done. Okay, so in terms of the setup, I guess everything is clear. We're going to be using this setup throughout, except one or two occasions again with SPL meters. Okay, so that was all clear. So the first thing that was of interest is to measure the correlation of multiple measurements with same source and receiver positions. Okay, so what can we say about this? What was the thing we found when we did multiple measurements with the same positions?
And after you correlated, it showed that like the low frequencies weren't very reliable.
Yeah.
And the high frequencies got slowly less reliable.
Yeah, exactly. Okay, so the reason for doing that is to understand the baseline. In fact, the one of the baselines, because there are further ones. Okay, so we understand that for some reason or other, our measurements are not very reliable at low frequencies. What was the cutoff for reliability in different groups? Does anyone remember? Did we know that? Those would have been, yeah? Those would have been the kind of the interesting things to take forward.
I find that it was around 90 hertz or above.
About 90 hertz, yeah, somewhere below 100. I think in 71 I had it fairly low, already 60 or something similar. Yeah, so you see, I mean, in your assessment, which will be a portfolio of measurements, if you want to do it well, that's definitely one of the things to consider. Okay? Do a basic comparison of measurements taken in the same position in order to establish the baseline and in order to be able to say, well, actually everything below that or above that is a bit random. Okay? What you can do as well, if you want to be a bit more accurate, you can say how bad it is, which you can express in decibels. So we've heard there is an increasing problem with increasing high frequencies. So you could also make an estimate of that and say that, so you can imagine a situation where I say, well, actually there is a 13K peak, which is 10 dB, okay? And then you should be able to say, well, based on my baseline estimation, at 13K, I have about 7 dB problems, variety of measurement variance. Therefore, I assume that this 15 dB peak still tells me something, right? If you have a 7 dB peak at some high frequency, and your baseline estimation says that this is the amount of randomness you get anyway, then there is no ground for claiming peak. Okay, so that's that. And then also there was something about the averaging of the graph, right? So you have seen graphs with no averaging, which had a lot of detail, a lot of spikes and dips.
Sorry?
Averaging.
Oh, right.
And you've seen different smoothing, I think it's called in fuzz measure, at an octave, third octave, and otherwise. So why would this be useful? What's useful about having both? Well, it's hopefully going to transpire today when we are looking for peaks and troughs that we know where they should be. Because in a way, you see, if you have this very detailed graph and you identify a peak, let's say, right, you would want to know what is the extent of this peak in dB. So then you can take the averaging one, which will give you the average value in the vicinity, and then you can express the dB of the peak in relation to the frequencies nearby, right? So that's something we will probably see happen today. Okay, so you figured out the correlation bit. Okay, so it's kind of telling us the difference between two graphs. Now this idea, this technique of looking at difference between graphs is crucial, right? Because we don't have anechoic chambers, we don't have calibrated mics and speakers. So in essence, everything that we attempt will be some kind of relative measurement. We're going to try to express things relative to the other measurement because we cannot claim anything absolute. Okay?
That sounds like an absolute statement to me.
It does sound like an absolute statement, yes. There is one thing though. Would anyone like to contest what I've just said? Because there's one thing where we can make it absolute, which is what you played with in the first practical, the SPL meter. Okay, so the SPL meter is calibrated. Okay, so how could this be potentially useful? Well, we won't obviously quite analyze a spectral response of a loudspeaker, because for that we would need all the calibrated gear that we don't have. But what we can do is we can, for example, estimate the amount of distortion from a speaker, again relative in relation to the amplitude. Okay, so that's one of the things that no one really asked last time. I kind of didn't imply it a needed question either. But if you're trying to be accurate in this domain, my instruction of about 30 dB about noise floor should have rang some alarms, right? Because it's not very accurate, and in this domain we could set an absolute SPL. Okay, so it is a question whether this is meaningful, and the answer will depend on the type of measurement we perform. So as soon as we get into harmonic distortion, right, it might be really important to know what is the absolute SPL. Okay, so briefly, measure the correlation when swapping source and the receiver position. So can anyone tell us what the hell happened there? So we had two exact same positions, just swap the speaker and the microphone. What happened?
So in our correlation, when we did that, it was like it became more consistent towards the high end of the graph. Which I'm looking at again.
Okay.
The correlation was less reliable in the middle, and more reliable at the end is more correlated. But the base was still useless. It's still very
That's interesting. Any other remarks, comments? Does anyone remember what happened? Would anyone like to reflect on what they would expect based on understanding of theory?
Yeah.
Yeah?
So if you switch the position of the speaker, you're switching its relative position to the room, so you might get certain, how would you say, without saying amplification of the signal?
Resonances.
Resonances.
Yeah. Peaks and troughs. Yeah.
depending on the
Because
shape.
if it's close to the wall first, and then further in the second, you can have a.
And why is it different from having the microphone close to the wall?
Because speaker radiates more energy. Actually, radiates energy while microphone receives it.
Yeah, I can agree.
So it interferes
Yeah.
with the room compared to the microphone, which is.
Yeah. So that's one thing that we'll see if we get the time to do, but there's not many practicals, unfortunately. But because we could, actually, I think I can squeeze it in next week when we deal with the rooms. So once we discover the resonant mode of the room, typically an axial mode is the simplest thing. What we can do is we can see, can we excite that mode more and less depending on the position of the speaker. Okay? And you can already predict, well, it's not your prediction, you can count on one of the portfolio tasks to be speaker position assessment and optimization. Okay, so that's the kind of thing I imagine everyone wants to do at home. And we can do it with fuzz measure demo as well. Okay, cool. So swapping, it's actually another baseline thing to consider, right? In terms of unidirectional energy propagation in that sense. Okay, and then we had correlation of distinct but comparable sources. So you see, now that we are revising this, what do you feel the need for? What is it that you should have done last week and you didn't do?
Save all the correlations.
Yeah, but looking at these graphs right now would probably also not be the ideal thing. What would your notebook contain? What would have been the crucial things? So we had the cutoff points,
Yeah.
right? Anything else? Yeah.
Actually, like measuring where you are in the room and writing that down.
Yeah, but is that? I mean, it is something that would provide more detail in that sense. But the question is, in this discussion, in reflecting, in progressing, would that information 1.2 meters from the wall actually add to this discussion? A little bit, not horribly. Yeah, something around that. Not horribly. What does that even mean? Okay, but what would definitely be a good
Room dimensions.
set of notes? Yeah, room dimensions maybe. I mean, that would be useful if we were start to compare things. Okay, so one thing that I would actually be interested in comparing would be, okay, what did we get in 171 in terms of the cutoff point? And what would we get in a dead 150A in terms of the cutoff point for reliability? Because that would be something I want to take away home, right? And I know, okay, so now I'm in a big room, because actually for me in 71, it was only below 60 hertz that it started to freak out, right? So I could actually take that home and know that, okay, next time I'm in a huge room, I can actually look down up till 60, 70 hertz. And if I'm in a small one, maybe it's slightly higher up, right? So these kind of building hypotheses activity would be quite interesting. Anything else?
About the question.
About what would be really useful to have now in terms of reflecting on last week's practical, in terms of notes. Because I kind of left it open. I said, if you find something cool, just post it. Okay, so I'm kind of choosing this also to, stimulate your thinking more so than following instructions. Because if I told you, okay, note this, and that, you'd be mechanistically noting things down and okay, you've done it. But I think this is more interesting to actually consider what would have been a good set of notes. So what else?
Sound treatment in the room.
Yeah, so in terms of comparing different rooms, it would be great to know, okay, a dead room, in terms of reliability, this and that. What I'm aiming at, actually, is dB values. Okay, so just, a dB value, for example, that would say something about the difference between a speaker in the corner and the speaker in the middle of the room. And it's again, if you have a full graph, it's kind of tedious to maintain all these graphs, to reread them, to remember which room, what room, match it against the room dimension notes, match it against the absorption material notes, right? So you don't want everything. I mean, if you have everything, you probably never look at these notes again. And if you have a few good realizations, you probably don't even need to make a note, you will remember it. Because it's, oh wow, I figure it. A larger room, I can rely on lower frequency measurements, for example. Okay? Or indeed, actually I realized in a resonant, reverberant, whatever, 71, I get, in the corner, I get 10 dB extra bass.
So there's
In a treated room, I get only 5 dB extra bass, or is it 7 and 2? You know, just to get these ballpark things in your head, because that actually improves your practical understanding of the matter. All right? Yeah?
So something we found in our group interesting, we realised whilst moving the speaker and the receiver around the middle of the room,
Yeah.
which is all quite similar,
Yeah.
and we're like, oh yeah, because the room's square, it's quite symmetrical.
Right.
So of course there wouldn't be much of a difference
Yeah.
playing around with just like the middle of the area,
Yeah.
which makes sense based on.
Yeah, exactly.
Yeah.
Yeah, yeah. So the only thing added to that would be a note which says, okay, so what is crucially different if the speaker is not in the center of the room? And typically it would be some increase in bass, how much, where is the cutoff approximately? You know, get those things, because, you know, you won't find it in the textbooks really like that. And it really kind of improves your understanding of things at hand. Okay, and then we also looked at producing an average graph. So actually the things that we've done are crucial. So correlation graphs, which you can consider the difference between two measurements, and averaging graphs, which you can consider the sum of multiple measurements. Okay, so did we have anything cool come up there? Average graph of dramatically different source and receiver positions. So the question here, what I've suggested, which was not horribly accurate, is that if you average multiple measurements at different locations in the room, you will start to get some characteristic of the room crop up. Is this true statement or not?
Yes.
Why?
Because although like the overtones, I like the apparent frequencies of the room might like slightly change, shows you that basically the reflections are still working kind of like the same.
Okay, so first of all, reflections are not working the same because they depend on source and receiver positions. What it is that works the same? How do we call this? The room modes.
Yeah.
Okay, so the modes are the characteristics of the room that are supposed to prevail, right? The thing that happens due to direct reflections or first, second order reflections are typically very much dependent on the positions. Okay, and there was one other thing, I should have probably started what you said at the beginning, which was also, you used the term overtones.
Mm-hmm.
What does the term overtone mean?
The harmonic series.
Not only. Okay, so that's part of instrument acoustics. Okay, so all the harmonics are overtones, but not all overtones are harmonics. What-
Overtones, isn't it true that like basically when, for example, you pluck a string or something, all of the notes are being played, but the overtones are the ones that we actually hear, like with chords,
No.
for example,
No, there is no such thing as all of the notes being played.
all of the
That-
frequencies,
What all of the frequencies?
like with color, right? Like when you watch a gray color, it's basically like it has certain pigments that like being like reflected back to you, which are like color frequencies.
No, the analogy is not appropriate. If you pluck a string, you will get overtones. Depending on the thickness of the string, they will start to deviate from harmonics, by the way. The thicker the string, the more stretched set of overtones you get. So a thick bass string on a piano has stretched harmonics, and when you tune a piano, you do the stretch tuning, so you actually stretch the whole scale to kind of match the timbre of the lower bass strings, okay? An ideal string has strict harmonics, okay? And has all the harmonics. An ideal ruler or a pipe with one end closed and one open has all the odd harmonics, okay? And as soon as it's not ideal, there is rubbish as well, okay? A good example for overtones which are definitely not harmonics is
Resonance?
in the, no, resonance is a physical phenomenon, is in the spectrum of a bell. Okay, that's your textbook in harmonic spectrum. Okay, so bell has overtones, but they are not strictly harmonically related to the fundamental or to the fundamentals. You can probably even argue that they're multiple. Okay, so in this context, actually a room mode has its overtones. It has its harmonics. But the way you've used this term was not appropriate. Cool. So we are thinking about this averaging. So you said yes. Would anyone like to contest that? Is this a strictly true statement that I will start to see room modes appear?
I think you would start to see trends, but
What other trends I will start to see? We're getting there. So supposedly after a while, the random or the variation due to positioning will flatten out. We can kind of assume this. We can assume that the room modes will not flatten out. What else will not flatten out? Crucially.
The room decay.
We're just looking at the spectral response now.
Well, the speaker.
The speaker and the microphone. Okay, so they are also constant. Okay? Could you think of a way to reduce that effect?
what do you mean constant?
Well, you see, because what you have is when you create multiple measurements, you average them out. The things that are constant across multiple measurements will start to become prominent in relation to things that are varied, right? So things, just a second, things that are varied will be the things that relate to the position of the mic and
Are
the
you
speaker.
suggesting- Would the solution then to be to change speakers and
Exactly.
microphones?
Yeah,
I see.
that's it.
I see.
Yeah, so if you have a set of 5-6 different speakers and 5-6 different microphones, and you do a merry-go-around combinatorial exercise with those, with all the positions in the room, okay, slowly but surely, we will actually get only we will converge to the peaks which are essentially due to the room. Okay?
Is there an easier way to do it? If we perhaps.
Yes,
have
calibrated
access to
gear.
yeah.
Calibrated gear.
Ah.
If you have calibrated gear, then you know that that's the case. I mean, you've all seen the calibration chart for the microphone, the MM1, right? It looked fairly flat, kind of a bit louder in the highs, right? But it is the case that the speaker is worse. In fact, I think we will try and bring it out one of these practicals. I think we will do one practical when we kind of collectively measure stuff, probably in 88. We have an Omni speaker as well somewhere in the which has I think 8 membranes pointing in all different directions, right? So it kind of saves you from putting speakers and orientating it in different ways. By the way, I remember one group was actually playing with the orientation of the speaker. Would anyone like to say something about that? What was crucial? I mean, it wasn't part of the task.
It was the off-axis response of the speaker as well.
Yeah, it's the off-axis response of the speaker, which is typically what?
Bad.
Bad, namely, just losing highs.
Yeah, we did that. We literally put the speaker facing the corner.
Yeah, and you
it,
just
it proved that theory.
you just lose the highs.
It's just lots of bass.
And that's another thing, you see, so that's why I'm trying to inspire you more than have you do stuff. Would you not want to know how much softer is the 10K at the side of the speaker? You know, just have a ballpark. Is it 3 dB or is it 10 dB or is it in between? You know, these are the kind of things you really want to get interested, because that will give you your understanding of what the hell to expect, what's going on. You know, and if you do a measurement at one point in your career, it's not just like, okay, well, there is the graph. You see, that's typically also an issue with a lot of final year projects which use some graphs. It's like, there it is, self-evident in it. Well, it's not, right? And for you, if you see a graph and you know what it is, if you have these ballpark values stored, you know what to expect, then you immediately know how to read the graph. You're like, oh, wait a minute, that off-axis response of the speaker is funny. Is it a lot of highs on the side, or is it just too few highs compared to what you might expect? So this is what we're really after, kind of learn the domain, learn what to expect. Okay, I think we've covered that. So we're gonna go briefly through today's bit. We're gonna do 6 groups. So maybe you'll be 2 in a group, which is actually the ideal group size, I think. But maybe some 3 groups. I guess you're kind of spatially arranged already, just based on acquaintance preference for deodorants, or I don't know why you stick together the way you do. So find your 6 groups. There is the instruction. So I will just go briefly through it. So what we're gonna do, you don't have a group?
No, it's always pointed at well.
Go ahead, it's 2 to 3. Whomever you prefer. Okay, so everything will be fairly comparable. Could I have some attention? Okay, so let's just briefly go through this and then you're off. So same gear, additional bit of gear that you will find is a tape measure. Okay, so what we're going to do today is we're going to assess sidewall and rear wall reflections. Okay, now for those of you who will be in the 50 room, you might find that the walls are treated. Okay, so what I suggest is you use the desk as your reflective surface. So what I will discuss in terms of a sidewall reflection, you can actually map to a mixing desk reflection. Okay, so the first thing will be to create an equilateral triangle of each side being 1 meter. Okay, so I have a microphone, which is a distance to the speaker 1 meter, and the triangle which connects the microphone and the speaker via the wall should also be 1 meter each. Okay?
So essentially, you want us to have mic, speaker, wall, and
And-
equilateral, like same
Yes.
side. Okay.
Yes, all the same sides. I thought this would be the simplest thing to set up. I mean, we're not quite studying geometry and, constructing triangles. It could be cool. In fact, there's a bit where you can engage with that. But this will be our basic setup, okay? 1 meter each. Okay, and then we're gonna measure, right? So, first question, what is the path length difference for the reflection? So remember me in the lecture going on about path length differences. That will give us the crucial value. And in this case, how much longer does the sound have to travel via the wall in this situation? How much longer, you see, because you take the difference of path length. That's what we're after. So the path length between mic and the speaker is, I just defined it, how much?
Was it 5? Was it 1 meter?
1 meter, right? I have a speaker here, microphone here, this is about 1 meter. It is an equilateral triangle, meaning that the distance from the speaker to the wall in describing what we call a specular reflection is 1 meter plus 1 more, 2 meters. So the path length difference is
It's 1. Wait, it's then 5. So, well, 1 meter.
1 meter. Okay? Because it takes 2 meters via the wall, it takes 1 meter directly. The path length difference is 1 meter. Okay? So how do we figure out what is the frequency notch? At what frequency do we expect a notch? What is the phase difference that is necessary for destructive interference?
So it's
180.
180, yeah. which is half the period. Okay? So it means that 1 meter has to be half the period. Make sense? So full period is 2 meters. So the question is, which frequency has a period of 2 meters, which depends on speed of sound in the medium, which we can assume to be 340 meters per second. Okay? So the question is, which frequency has a period length of 2 meters on planet Earth at room temperature? Well, can we work it from the hand? So it's 340 meters per second,
Yeah.
right? So I will travel. How many seconds does it take to go 2 meters? It takes 1 second for 340.
1.72.
So 1 over 170. Yeah? 1 over 170 is the amount of seconds it takes to traverse 2 meters, which is the frequency of, hallelujah, 170. Because frequency is 1 over seconds. Hertz is 1 over seconds.
So basically that's the frequency that's supposed to be destructive in a sense?
Yes,
Right.
if I've got it right. I didn't sleep very well last night, who knows? Don't trust me. I'm not a priest. You have to approach me skeptically and you have to verify everything I say.
So it's 1.72.
Yeah.
Do you mind writing those down?
No, I mind. I don't write those down. I'm in fact doing you a favor by talking you through this, which will help you think through this on your own. That's the point of your studies. It's being able to think through this. Yeah, exactly.
I just want the equations written down.
Oh, we have it in the slide.
That's all on the slides already.
Yeah, but
It's uploaded. Yeah.
I think I can.
I know, but I just don't want you to resort to, religious attitude towards my slides. I want you to fortify.
Equals velocity divided by wavelength. Just like then you place the factors.
Okay, so you understand how to get there. And I would hate to stipulate out the path. I want you to try and get there yourselves. And evidently I will be visiting all the groups, so I will help you if you get stuck. Yep.
If the frequency is 72 divided by 1, so that's the frequency in hertz, right?
What do you mean 72 divided by 1?
I mean like 1
Over 72. Why 72?
Sorry, 1 divided by 1.72.
Yeah, so
This
that's,
is in hertz.
Yeah.
yes, the reciprocal of time is hertz. Yeah. Okay, so you've got the thinking process.
Yeah, okay.
You have an idea.
Then it's from the.
Okay, and then finally verify. Guys, please.
Yeah.
Someone,
Sorry.
thank you. So finally verify the estimation with measurement. Okay? So the interesting thing will be, note it down. Can you identify this notch around 170? And if you can, note it down very accurately. Because one thing is to start learning your own ballpark values, but the other thing is to be able next week in this same situation when we discuss, and I say, okay, who's got 170? Oh, we had 172. Then we start to learn from other groups' activities as well. Okay? Again, I won't force this, I've had really bad experience with and I guess you too, with pages of instruction that you have to go through, and by the end of it you don't remember anything and you don't feel like you've learned anything. Right? So I'm deliberately avoiding very specific instructions, which is the reason why I lost one of the modules in the past, but that's fine. Huh?
Which one?
APDI. Okay, right, so we had that. That should be fine. Number 5, make the same arrangement with a less reflective surface and measure the dB difference of the notch. Okay, so now hopefully we've got the notch, and now we're looking at replacing the reflective surface with something less or more absorptive. So it will depend a lot in which room you are. Lucas wasn't happy with you taking a piece of wood because it's sharp and you could cut yourself. So you will have to improvise, but maybe putting a table on the side or something. I mean, these are fairly reflective walls. Just see what you can do. Okay, try to get a different surface. Again, it's a ballpark thing. Just to see, okay, first of all, how deep is the notch and how deep is your love? And then to see how is it deeper or shallower with, and how much with a different surface. Okay, so that's again something that will have hopefully some value for you once you consider treating your side reflections in a studio or at home. Okay, so a different surface. Number 6, consider to have a pair of speakers with an unfortunate hump at 100 Hertz. Okay, so if this really causes a headache, skip it. Okay, don't worry. But this is a kind of a brain exercise, more than measurement exercise, but it relates. So if you want to be brainy, go for it. So just a sec to finish. So what we are assuming, we have a hump at 100 Hertz. We want to find an arrangement whereby we get a dip at that 100 Hertz due to speaker positioning. So now we know something about the speaker, and now we want to alleviate that issue with positioning, which is much better than with room correction software, for reasons we will get to. Yes?
Forgive me if I'm going to re-explain this, but I just
Please.
want to get like the
Yes,
actual
yes, for sure.
concept. So you're asking us to get a speaker that peaks around 100 Hertz?
No. This is a mental exercise. I don't have a speaker for you. No. You don't actually. I mean, you should try to think of it. So it's kind of going to expand on your ability to consider some geometry.
Okay.
So we can go briefly through this. How would we do this? What's the first thing we can figure out if we know it's a 100 Hertz problem?
Distance.
Yes, namely, what was the exact term I'm using deliberately?
The speed.
Path length difference, right? So from this frequency, we could estimate the needed path length difference. Now, once we have the path length difference, it's not over yet. That's when the geometry kicks in, right? Because typically, I'm not equidistant from the wall. This equilateral triangle is the simplest case scenario, but typically in a studio, speakers are nearer the walls than myself, right? So if you really want to play this game, and why not, it's a good exercise, what you would need to do is say, okay, my studio is 4 meters wide, and now do the exercise. You get it? Because if I know that it's 4 meters wide, and I want a notch at 100 Hertz, I have 2 variables left. One is the distance of the speaker from the walls, and the second one is my distance from the speakers. So if you have these 2 variables, you'll probably consider your distance to these speakers to be more or less fixed, right? Because of the spectrum, because of many things. So when you fix that, then you can figure out, okay, can I produce a path length difference? You get it? It's increasingly complex geometrical problem at this stage. But what you can also do, you don't have to come up with an equation. It will probably take me half an hour myself. I haven't done this for quite a while. Just to come up with the equation with the variables, and then you insert the variable and it spits out the value. What you can do is you can do ballpark values. So you can say, okay, let's just say it's 4 meters. I'm 2 meters from the speaker, and the speaker is 1 meter from the walls. Let's just calculate this basic situation. And if you can do this quickly, then you can say, okay, it's too low, it's too high, how about I move it? So you can kind of experimentally get to it. What's the other way to get to it?
Calculating.
This would have been the first one, second one experimentally.
Listening.
Listening and measuring in terms of acoustic measurement. Okay? Because you can do the same thing like you're going to do now. You're going to try to find the 170 Hertz peak, and you know, okay, I'm going to try to move the speakers within the room to get the notch at 100 Hertz. Well, keep moving them until you get the notch. In fact, you see we are using 1 second sine sweeps. That's fairly quick. You can actually go back and forth, move the speaker maybe within 30 seconds. And if it's 2 of you, one is stood at the speaker, give us a bit more, give us a bit less. Right? Cool. If this was an acoustics class 30 years ago, they would probably execute me for the methodology options. Okay, so that was that. And number 7, measure the distance of a speaker to a rear reflective wall. Okay, so we had a side reflection. Now we're going to look at rear reflection. And what we're going to look for is humps, right? So we looked for the dip. By the way, for the dip, you should also be able to verify the comb filter shape. So another thing to think of is, okay, I find the dip in dB. Are all the other comb dips of the same level? Do they climb up? Do they climb down? Interesting things to discover there. So once we have the side reflection, we're going to look at the rear wall reflection, and we're going to look for the hump. So the rear walls are typically nearer and typically give us an uncomfortable bass boost. Okay, so we're going to work around this phenomenon. So same thing. I will ask you, so depending on the studio that you're in, you can measure the distance. So essentially, obviously this is very close, but what you would prefer to do is estimate the distance of the bass membrane. Obviously we're dealing with bass frequency, and the kind of the cone, the front end of the cone. So it's not the front end of the baffle, it's slightly deeper, maybe 3-4 centimeters deeper. But you see here we're really close to the wall, so those 3-4 centimeters may count quite a bit. Okay, so here probably you are in a studio that has a speaker to start with, yeah?
But okay, so we're mostly calculating from the back reflection, we're mostly calculating the bass reflections, as you said, right?
Yeah.
Okay, so the thing is, the speaker is not like stuck totally to the wall, it's like with a brace, right?
There is a distance, yeah.
Yeah, and wouldn't that actual brace make a big difference in how much bass is reflected off the wall?
Yes, that's what we're after.
Yeah, like
So the
it's
distance of
lost.
the speaker to the rear wall is crucial.
And maybe
Especially with the rear ported speakers like
and
this.
maybe
You're
also
not
the
supposed to do
material
this.
of the hook itself, like, or the thing that's hanging
No,
the speaker?
no, we're not. I mean, it could resonate, it could cause problems. It is, you can call it,
more or less bass to the
it's a
wall.
coupling to the wall.
Yeah.
And the wall, so this coupling will actually allow vibrations to travel faster, as you know. It's in a solid, right? So you could say that the vibration will get to the wall quicker through the brace. The thing is, it won't get out of the wall that easily. So if you remember, you know, if I have structure-borne vibration, right, it's not really easy for that to escape the structure. It has another impedance boundary, right? So, for example, if I have this, let's say I'm shaking this table, right? And let's say I'm shaking it at 50 hertz, which I'm not, but who cares? Imagine it, but you still don't hear it. How would you make it audible? Oh, just put a resonant object on top, right? So the structure-borne vibration doesn't exit the material that readily. I mean, it could be, it's an interesting thing to consider. Would that add or subtract? How would you find out?
Again, sorry,
How would you find out the brace, whether brace has any significant effect?
You use different material.
You use different material, you remove the brace, you do the same distance from the same type of wall
If you could just
on brace, without a brace. Please don't remove braces here, okay?
No, no.
So this will be potentially tricky because some studios you won't really be able to move the speakers at all. So it is up to you. Probably best if you just do it with the stand and the speaker that's already set up. But if you're interested, you could as well do it. In fact, if anyone is in 171, that's the one place where we have speakers bang against the wall. And it would be interesting to know how bad that is, or whether it can be better. So we're going to do a similar thing, but with the difference that now we're going to have a speaker with the back wall, and we're going to measure the distance, and then try to do the same thing. So we don't put it deliberately at a given distance. Okay, so we estimate the hump, measure the hump, verify the hump. Okay, and then what I will ask you to do is do 2 more distances. Okay, so maybe like close to the wall, 10 centimeters, kind of away, 40 centimeters, maybe 60, 70, and like proper, almost deep in the room, 1 meter or more. Okay, get these three things, try to do the math, try to verify the humps. Okay, so that's that, and then the biggest brain exercise will be, what the hell? Both are reflections. Why are we looking at humps and dips alternatingly? What the hell is going on here? Okay, so I won't answer this question. This I leave you to ponder upon. I will talk about it gladly with every group, but most of all, I'm happy to discuss it next week when we talk about everything. Upload your interesting results to Blackboard, upload it to your brain, all the rest, pack up the gear, sign it off. Okay, any questions? Cool, guys, off you go.